Hello Honors Pre-Calculus students, Mr. Gazzato. The learning target today is to solve problems involving permutations. The definition of a permutation is on the screen. A permutation of n different elements is an ordering of the elements such that one element is first, one element is second, one element is third, and so on. The important word here is the word ordering, and I'm going to underline that in red. And let me give you an example. If we're in a race and Miss Gilbert is first and I am second, that is different than if I am at first and Miss Gilbert is in second. So the ordering of the objects or the elements is important. We're going to take a look at several examples throughout this lesson. Let's take a look at the problems on the screen. In problem number 1, how many ways can everyone in the class line up? So first, let's assume that there are 24 people in the room, including the teacher. So if we were all to line up at the door single file, how many ways can that be done is the question of interest. Go ahead and pause the screen and try problem number 1 and then come back. So if we think about problem number 1, I'm going to draw 24 dashes, 1, 2, 3, 4, and so on. So there are 24 people in the room. So for that first spot right there where I put the blue arrow, there are 24 choices. Suppose it was Tom. The next spot, there are only 23 choices. Suppose it was Tammy. The next choice, there are only 22 choices. Suppose it was me. The fourth choice, there were 21 choices, and so on until you get all the way down to 1. So we learned in the last lesson we could write this as 24 factorial. And then just to repeat how to do that on our calculator. So on the TI, it's 24 math, move over to probability, and you press number 4. And this number will be in scientific notation, 6.204 times 10 to the 23rd. So this is approximately 6.024 times 10 to the 23rd. On the Casio, to remind you how do you get to this menu with the factorial, you're going to type in 24, option, F6, probability, F3, and then you're going to type in F1, and you'll see you get the same answer. So that's how many ways 24 people can line up at the door. For problem number 2, let's suppose that Mr. Gazzato and let's for this particular example, let's suppose Miss Gilbert is in the room. So how many ways can we line up at the door? There are still 24 people, but Miss Gilbert and myself must stand next to each other. So now let's think about we have 24 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and then I'll say C and G for myself and Miss Gilbert. So now consider this, how many objects or things are lining up at the door? So I'm going to circle myself and Miss Gilbert. So now if we were to count, there are 23 objects lining up at the door. So for problem number 2, we would say 23 factorial. But then Miss Gilbert and I, we are standing next to each other, but we can switch. So how many ways can we switch? We need to multiply that by 2. So then using your calculator, 23 factorial, and I just showed you how to do that, times 2 is approximately 5.17 times 10 to the 22nd. Let's look at problem number 3. So for problem number 3, again, let's assume there are 24 people. And for this particular problem, let's assume that Miss Gilbert's in the room and Mrs. Sankin. So we'll say Miss Gilbert and Mrs. Sankin. So how many ways can all the people line up in at the door, but the 3 teachers in the room must stand next to each other? So I'm going to do that problem off to the side here. So we got 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I'll put C for myself, G for Miss Gilbert, and S for Mrs. Sankin. So now if we consider the 3 teachers in the room as a group, how many elements are lining up? So if you count the dots and you count what I just circled, and I'm going to highlight this in yellow for emphasis as a group, how many objects are lining up? So for problem number 23, there are 22 objects lining up. The 21 dots plus the group that is highlighted in yellow. So that would be 22 factorial. But then consider myself, Miss Gilbert, and Mrs. Sankin. How many ways can we be rearranged? Well, let's list that out. I could be first, Miss Gilbert, Mrs. Sankin. I could be first, then Mrs. Sankin, Miss Gilbert. Maybe Mrs. Gilbert or Miss Gilbert was first, then me, then Mrs. Sankin. Or maybe me and Mrs. Sankin switch. Or maybe Mrs. Sankin was first, followed by me and Miss Gilbert. Or maybe me and Miss Gilbert switch. So if you look what I just wrote here that I'm putting this box in blue, there are 6 ways that we could be rearranged. So I'm going to multiply by 6. And some of you might be saying, well, that 6 is really 3 factorial. Because how many ways can the letters C, G, and S be rearranged? So if you just consider C, G, and S, you have 3 choices for the first spot, 2 choices for the second spot, 1 choice for the third spot. So when you type this in your calculator, 22 factorial times 3 factorial, you get approximately 6.744 times 10 to the 21st. So going back to problem number 2, technically, this is 23 factorial times 2 factorial, but 2 factorial is 2. So let me add an extra question here. Suppose we said 4 people needed to stay together. So problem 3A. 4 students, or excuse me, the 3 teachers and 1 student needed to stand next to each other. So then if you consider the red dots, and I put another student with the red dots, that means there would be 21 objects being lined up. So it would be 21 factorial. But then the 4 people that are standing next to each other could be arranged for factorial. So doing that on your calculator, 21 factorial times 4 factorial, you will get approximately 1.226 times 10 to the 21st. Let's take a look at the next problem. So for problem number 4, let's just assume that there were 10 boys and 14 girls. So how many ways can the 10 boys and 14 girls be rearranged or stand in a line where all the boys are together, all the girls are together? So right now, there are 2 groups. Okay, so there's boys and girls. So you get boy, girl, or girl, boy. So that's 2. But then, the boys could be rearranged. How many ways can the boys be rearranged? 10 factorial. How many ways can the girls be rearranged? 14 factorial. So, for problem number 4, you would do 10 factorial times 14 factorial, but then the boys and girls can switch, so that's why we need to multiply by 2. Doing that on your calculator, and Casio's, you guys have a little easier time, because you don't have to keep pressing math, probability, factorial. But doing that on the calculator, you're going to get a large number, and we're always going to write it in scientific notation. So 6.327 times 10 to the 17th. Let's take a look at problem number 5. Let's take a look at problem number 5. I have modified it a little bit because I started out with teachers also being in the room. So what if the sophomores, juniors, teachers, and seniors needed to stand next to each other? So for problem number 5, let's assume that there are 3 teachers, myself, Miss Gilbert, and Mrs. Sankin. For sophomores, let's assume that there are 8. For juniors, let's assume that there are 7. And since we're going to continue this from the previous problem, that there are 24 people in the room. Right now we're at 18 people, so that means there are 6 seniors. Let's assume you're in one of those categories. So let's just double check. Is 3, 8, 7, and 6, does that add up to 24? So 3 plus 8 plus 7 plus 6, that is 24. So we're going to line up at the door, and each group needs to stay together. Well, how many different groups are there? There's the teachers, there's the sophomores, there's the juniors, and then there's the seniors. So there are 4 groups lining up. Well, how many ways can 4 things line up, or 4 groups? 4 factorial. This is for the groups. Then we need to consider the teachers. Well, the teachers could be rearranged 3 factorial ways. I'll put T for teachers. The sophomores could be arranged 8 factorial. The juniors, 7 factorial. And then the seniors, 6 factorial. So I'm going to come down here to make this a little larger. So for problem number 5, I'm going to multiply 4 factorial for the groups, 3 factorial for the teachers, 8 factorial for the sophomores, 7 factorial for the juniors, and 6 factorial for the seniors. This is all the ways we could rearrange if each group needs to stand next to each other. Doing this on your calculator, you will get 2.107 times 10 to the 13th. For problem number 6, I need to draw a visual here. So for problem number 6, I'm going to draw a visual of the classroom. So let's suppose we have a classroom here, and there's the group of 3 teachers. Let's suppose I have a group of 4 students, another group of 3 students, another group of 4 students, a group of 3 students, a group of 2 students. So right now there are 5 plus 7 people, so there's 19. And then let's suppose I have a group of 5. So this is the arrangement of the groups. 3 teachers in the front, and then all the other groups. So question number 6 is asking, how many ways can we line up at the door if the groups need to stand next to each other? So if you count this, there's 1, 2, 3, 4, 5, 6, 7 groups. So the 7 groups could be arranged 7 factorial. Then you could rearrange each group. So the first group could be arranged 3 factorial. Second group, 2 factorial. Third group, 5 factorial, and so on. So then it'll be another 4 factorial, 3 factorial, 4 factorial, and 3 factorial. So this is what I would need to multiply in order to get all the different ways we can line up at the door where the groups need to stand next to each other. So let's type that in our calculator and let's see what answer we get. So provided I don't have any typographical errors, I get 1.505 times 10 to the 11th. So problem number 6 would be all the ways the groups need to stay together. And for clarity, these are the groups that I'm highlighting in yellow. And because there are 7 groups, I need the 7 factorial. And then rearranging each group are the remaining values. Let's take a look at problem number 8. So when my son was younger, he had 11 different Furbies, and I have some pictures of the various Furbies he had. Let's assume all the Furbies are different. And every night he would line up 4 of them. And sometimes his sister would go in and kind of rearrange them, and he would get upset because Max considered a specific arrangement to be different to him. So I'm going to use the dash method here. I'm going to draw 4 dashes. And for the first Furby, Max had 11 choices. Then he had 10 choices, 9 choices, and 8 choices. So then you could pull out your calculator and multiply those together. So when you do that, you get 7920. So there are 7,920 different ways he could align the Furbies. Every year a student says, well, can I rewrite it with factorials? Right? Every year someone says, yeah, I could rewrite that as 11 factorial over 7 factorial. And some people have a hard time understanding that. So what we do is we write that out. 11, 10, 9, 8, 7, 6, 5, all the way down to 1, over 7, 6, 5, all the way down to 1. And hopefully you see the 7s down reduce, so that is equivalent. So every year there are people that always say, can I type it in this way, 11 factorial over 7 factorial? And the answer to that is yes, you will get the same answer. Let's take a look at the next problem. So if you read this problem, a family of 4 goes to the movie theater and chooses a row of 9 empty seats. Let's assume that they're going to sit next to each other. How many different seating arrangements are possible if the family chooses 4 of those 9 seats? And for clarity, if I'm sitting next to Mrs. Cazzato and then it's Max and Carly, that's different if it's Mrs. Cazzato, Carly, Max, and then I'm at the end. So the arrangement is significant. So again, I'm going to draw 4 dashes. Okay. And when we go into that theater, Mrs. Cazzato has 9 choices. So I'll just say 9. I then would have 8 choices. Carly would have 7, and Max would have 6. So then you could pick up your calculator and type that in. Like the previous problem, some people say, could I write that as 9 factorial over 5 factorial? And the answer to that question is yes. And just to convince people, and every year it takes some time, if you were to write this out, this is 9 times 8, 7, 6, 5, 4, 3, 2, times 1. I'm going to fix that 1. Over 5, 4, 3, 2, 1. And again, hopefully you see that they reduce out, so that is equivalent. So when you do this problem on your calculator, whether you do it in blue or the factorial method, you will get 3,024. Let's take a look at the next problem. So for number 10, we're again going to use 24 people in the room, and we're going to pick a president, vice president, and treasurer along with secretary. So how many ways can this be done? So again, I'm going to draw 1, 2, 3, 4 dashes. And for clarity, if I'm president and Miss Gilbert is vice president, that is different than if Miss Gilbert is president and I am vice president. So if we switch roles, that's different. So for president, there are 24 choices. For vice president, 23 choices. The class treasurer, 22 choices. And secretary, 21 choices. And hopefully you've kind of deduced that you can't be in 2 positions, therefore it's kind of without replacement. And again, someone in class would say, well, can I write that as 20 factorial over, and what would this be? 20 factorial. And the answer to that question is yes. So go ahead and type that in, and let's see what you get. I personally just type in the blue. It's a lot quicker because I have a TI. You get 255,024 different ways we can pick a president, vice president, treasurer, and secretary. Let's take a look at the next problem. So in problem number 11, we're in a race, and there are 8 athletes. How many different first, second, and third place finishes could there be? So again, I'm going to use a dash method. For first place, there are 8 choices. For second place, there are 7. And for third, there are 6. So 8 times 7 times 6, 336 different first, second, and third place finishes. Again, someone in class may say, can we write that as 8 factorial over 5 factorial? And then the answer to that question is yes, and hopefully you realize that this is 8 times 7 times 6, 5, 4, 3, 2, 1, over 5, 4, 3, 2, 1, and you can see those reduce out, so you get the same answer. So for this last question, this was when the iPods first came out, and in the iPods they didn't have the random shuffling. So when you made a list of songs in an iPod when they first came out, it would shuffle them. And so Mr. Bonamy wrote this problem. Amy is his wife. So Amy had 34 songs on her iPod shuffle. How many different 5-song playlists can she make? And if Amy changed the order to Amy, that was important. So again, I'm going to do 1, 2, 3, 4, 5 dashes. So for the first song, Amy had 34 choices, then 33, 32, 31, and 30. For those of you that like that new method of factorials, 34 factorial over 29 factorial. And then typing this in your calculator, again, you could do either method, whichever is easier for you. You get 333,90720. So that's how many different 5-song playlists there are where the order is. So let's summarize here. The learning target today was to talk about permutations. So here's a blank slide. The number of permutations of n elements taken r at a time is, and now I kind of want to go back through all the problems and kind of compare and contrast them. So let's go back to number 8. For problem number 8, there were 11 Furbies, and Max was choosing 4 of them to line up. So I'm going to say this is 11 permute 4. That capital P means permute. So he's lining up 4 of the 11 objects. For problem number 9, we had a family of 4 going to the movie theater, and there were 9 empty seats. So out of the 9 seats, I'm going to say permute 4. For problem number 10, that was the class officer problem. There were 24 people, and I need to pick 4 of them for the different officers. For problem number 11, so this should not have been number, it was the Hornet race, and there were 8 people running in the race. So out of the 8, I need to pick or permute 3 of them for first, second, and third place. And then for the iPod problem, there were 34 songs, and she needed to pick or permute 5 of them. So what I'd like you to do is take a look at the green and compare that to the yellow. So look at these problems. So what I'd like you to do is take a look at the green and compare that to the red. So we have 11 factorial over 7 factorial, 11 permute 4. If I jump down to 24 factorial over 20 factorial, 24 permute 4. If I look at 8 factorial over 5 factorial, we said 8 permute 3. And then if you look at the last example, 34 factorial over 29 factorial, that's 34 permute 5. Is there a pattern? And the answer to that question is yes. So if you have n objects and you permute r of them, so you're lining up r objects out of the n, we say n permute r, and I want you to look at this and say, well, what's the formula? And hopefully you've realized the numerator is n factorial. And how do you get this 7? It's 11 minus 4. How do you get the 20? It's 24 minus 4. How do you get the 5? 8 take away 3. How do you get the 29? 34 take away 5. So the denominator is n minus r factorial. So this is the definition of the different ways you can rearrange objects, n objects, if you're permuting r of them. So now let's go back to the handout, and we're going to use this n permute r notation. So if you look at problem number 11, you could say for this problem 34 permute, this is number, so let's take a look at problem 12. For problem 12, we could say 34 permute 5. If we take a look at number 11, we could say 8 permute 3. For problem number 10, we said 24 permute 4. For problem number 9, 9 permute 4. And for problem number 8, 11 permute 4. And some of you may have noticed there is a calculator underneath calculator command. So if we look at the Casio, you will see NPR. So if we wanted to do problem number 8, we would do 11 permute 4. And notice that answer is the same, 7920. On the TI, we would do 11 math probability, and notice number 2 says permute NPR, and we would say 4 and hit enter. So we're getting the same answer. If we go back to the handout and let's take a look at a different problem, let's scroll down and let's do the race problem. So on the Casio, 8, press F2, 3. Notice you get the same answer. On the TI, 8, math, move over to PROB, and you press number 2, 3. Notice you get the same answer. And if we were going to do the last problem with the iPod Shuffle, we could do that. So 34. And remember the Casio people, in order to get this menu, you press Options, F6, Probability, which is F3, and then it pops up. So 34, let me hit clear. So 34 permute 5, and you'll get the number that I had. TI people, 34, math, move over to PRB, PROB, permute, and we want 5. So if you're more comfortable using this for your work that I just highlighted in yellow, that's acceptable. Some people liked to use that for their work. So 333900720. Some people liked the dash method, so they did the work in green. Other people liked the factorial method. Ms. Gilbert and I do not have a preference on which way you solve problem number 12 or which way you solve problem number 11. Your work is perfectly fine to be what I just highlighted in yellow, or this green work, or if you prefer, the dash method. All three methods work. So I hope you found this useful about permutations. Remember the main idea, and I'm just going to put a summary here. How many ways can you rearrange R objects, or N objects, take an R at a time? So we say N permute R, and that's given by the formula N factorial over N minus R factorial. Remember, ordering is important. Thank you for watching and have a great day.